So what we're going to look at is change of variables of multiple integrals. This is section 15.9 in the book. The idea here is to make something that's very complicated to integrate over into something that's very simple to integrate over. So I'm going to look at a really good example of this in real life of the Carnot engine. So this is from mechanical engineering. Um, and it deals with the work done by an Carnot engine. And what we have to do is find the area of these four graphs. We have to find that area, and that will be the work done by the Carnot engine. So what I've done is I have brought over, I have actually graphed some examples of this on Desmos, which is a pretty good site. And you'll see right away that this stuff gets very complicated quickly. So I have four graphs here of xy equals 2 is in red, and then xy equals 1.5 is in blue, xy to the 1.4 is equals 2 is in green, and then xy to the 1.4 equals 1.5 is in orange. And what you can see here is that we would have to find the area between all these. So where they intersect. And if you look, that's not an easy task because they intersect at different points everywhere. Like, for example, if you were going to find the area straight up and down, like with respect to x, you could start here and then you go down, 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 and then that's green over blue, and then all of a sudden it's green over orange starting here, and then you keep going, and then it's red over orange, and so it's three different integrals, and none of these are easy to do. So the idea is instead of dealing with this area in here, use a different color. Instead of dealing with this area in here, we can make it actually much easier, a much easier area to work with. And we've actually done this before using polar coordinates. So let me show you the equivalent. Let me get rid of this problem here. The equivalent of this in polar coordinates would be the following. So if you have a circle, so I went ahead and drew it. You have this circle, it's x squared plus y squared equals r squared. And you want to make it a simpler object to work with. This would be, the circle in this case would be the area I talked about before that was difficult to integrate with. This circle's not difficult to integrate with, but that's because we already dealt with actually some transformations are called. X equals r cosine theta and y equals r sine theta. You've already dealt with these, which is actually comes from this section. So what happens is you want to take the circle and you want to convert it to some sort of figure that's easier to work with. So in this case, it's a rectangle. And I've picked a new coordinate system, r and theta, to work with to make this easier. So one way is going to be a transformation from left to right, and then the other way is a transformation from right to left. We're going to call that the inverse transformation. So the transformation that goes from left to right is x equals r cosine theta and y equals r sine theta. And this is what you're used to in pre-cal. So let's see a little bit how this works. You probably were never shown this before, so it's kind of nice to see it. If, for example, you have theta equals 0, you are right here, theta equals 0. R can range however it wants. So this right here is, let's just call this A. So theta is 0, and R ranges between, let's suppose that the circle is a radius R, just radius R. R goes between, let's say R naught. So R naught and 0. So out here is R naught. This is that's the radius. So when theta is 0, on the right, r ranges from 0 to r naught. That's over here. And then let's suppose that theta is pi over 2. So when theta is only pi over 2, then we are right here. So on the right, this is where theta is going around in counterclockwise, and r is a radial line going, like if you look, what I'm talking about is down here. So let's do the green one first. When theta is 0 and r just ranges, x is just r, and y is 0. So that would be this line right here, this line right there. Y is 0 and x is just r, whatever r is, all the way up to r naught. Then, whenever we have, let's get rid of that, theta is pi over 2, so if theta is pi over 2, we get x equals 0, and then y is r. So that would be this line right here, that one, this line right there, all right? So that makes, so this it's not, we're not just dealing with the circle, we're dealing with the filled in circle. I forgot to mention that. It's the filled in disk, all right? And on the left, the rectangle is going to be filled in as well. All right, so now if you look at maybe theta is 3 pi over 2, or let's say just say pi, like that. So when that happens, when theta is pi, you get x is negative r, all negative r values, and y is 0. And so that would be over here, like that. And so what we're doing is we're going around the circle in radial lines. So it's like this. You're going around the circle in radial lines. Those correspond to going up this rectangle using horizontal lines like that. So the horizontal lines in the rectangle are mapped to radial lines in that circle, in that disk. All right, so now what happens whenever you, let's see if I can erase this. Now what happens whenever, okay, I went ahead and redrew it. Now that was when theta was constant. Now what about when r is constant? So when r is constant, we are looking at lines like this, like going vertically up or vertically down, either way. There's no direction. But now let's look at when r is 0. So r is 0 and theta is anything you want it to be. All right, well, when r is 0 and theta is anything you want it to be, x and y are both 0. So that line that I drew on the left that's in green goes right there to 0, 0. All right, now let's look at when r is always, let's say r naught out here, I don't know, let's say it's 1. So when you look at r as like a fourth, let's say, and theta can be anything you want it to be. So that's this line right there. When r is a fourth and theta is anything you want it to be, then what you have is that would be 1/4 cosine theta is x, and then 1/4 y theta, 1/4 cosine theta, sorry, is y. And so when you square these and add them, you get 1/4, you get 1/16. So you get a radius of 1/4, like that. Just square them and add them. You get 1/16, which is a radius, circle of radius 1/4. So now whenever you look at maybe when you're at 1/2, it's that line right there, then doing all this business here with 1/2 instead would be a circle of radius. Well, it's just up here actually. Yeah, x squared plus y squared equals 1/2 squared, which would be 1/4. So that would be a circle of radius 1/2. And now if you look at 3/4, that. So that would be x squared plus y squared equals 9/16, which is a radius of 3/4. So that's a circle of radius 3/4. So what happens here is the radial lines actually, these vertical lines become circles, and the horizontal lines become uh, rays. And so this rectangle here is completely filling in this circle here. So why work with a circle when you can deal with a rectangle when uh, it's a lot easier in many ways. It's a lot easier to work with a rectangle. All right. So that is one way that you actually have seen change of variables before. What you're doing is you're going from x and y to r and theta using the transformation. The transformation is x equals r cosine theta, and then y equals r sine theta. Now, in general, they use u and v for this, and so we will too. Let's do another example of this. This one's actually done in the book, where they give you a rectangle, and it's converted to this figure here on the left, on the right, in blue, using a certain transformation. So we can play around that a little bit. I'll do one of them. So let's look at when s is 1. So when s is 1, so we're dealing with u and v here, u and v. I'll tell you what, I'll redraw all this because it doesn't look very good. Okay, so I've redrawn the scenario there. So what we want to do is find out what's going to go on over here from this rectangle in this square, excuse me, in the UV plane. What does that look like in the XY plane? And what's going to happen over here is a region that we don't really want to work with. And so we're going to do a transformation backwards. That'll be much nicer to work with. In other words, we're going to work with this rectangular region instead. So let's just see a little bit. They're asking you to play around with this a little bit. So let's look along the bottom line here. It's in green. Let's see what happens there. So u ranges from 0 to 1, and v is always 0. So when that happens, x goes from 0 to 1, and x is u squared. And then when v is 0, y is going to be 0. So we're along the line y equals 0, and then x is u squared. X is going from 0 to 1, so that would be like this line right here. Y is always 0, so it's got to be on the x-axis, and x is going from 0 to 1. It doesn't matter how fast it goes. All right, now let's look at another one. Let's look at the vertical one between 1, 0 and 1, 1. So we'll call this one, we'll say this is in red here. So the one in red there is v equals 0, and v ranges between 1 and 0, and u is always 1. So when that's the case, over here, v ranges, u is always 1, so x is 1 minus v squared, and y is going to be v, if you substitute those in. So since y is v and x is 1 minus v squared, what this means then is x equals 1 minus y squared. And so that is a parabola that is sideways. Let's see here. If you move things around, it's y squared. Yeah. It's x equals negative y squared plus 1. Let's move up 1 and then upside down. And so u is always 1 and v goes between 0 and 1. Y has to go between 0 and 1 from this. All right, so that would just be this parabola here, where the top is 1. All right, so that bottom was 1. This was 1 here. All right, so that's a parabola like that. Now let's look at things in general. So if you look, the whenever at the top here, let's do a different color. Let's do this light blue. At the top here, U ranges between 1 and 0, and V is always 1. So when that's the case, it's x equals u squared minus 1, and y equals 1. V is y equals u. Sorry, y equals u. So taking these together, you get x equals y squared minus 1. And so that is a parabola that's opening up on the other side, or to the right actually, on the other side. It's that one there. And now let's just finish this out. Let me pick magenta here. Let's look at this line right there. For that line right there, what we have is that, let's see, u is always 0, and v ranges between 1 and 0. And so taking that down here, when u is always 0, x is negative v squared, and y is 0. Well, y is 0. Right, so we're going to be on the x-axis. We're going to be on the x-axis, and now see, since v ranges between 0 and 1, x ranges between 0 and negative 1. So that would be the line in magenta that I drew on the graph. It's this one right here. So what happens is the transformation, this transformation t takes this box and it transforms it into that figure there. So you might be wondering what happens in the middle. We looked at what's on the sides. What happens in the middle is all these parabolas that are going on. So if you want, you can take a particular line, let's say maybe this one here, where this would be v is a half, and u goes between 0 and 1. So when v is a half and u goes between 0 and 1, let's see what happens here. X is u squared minus a half, and then y is 1/2 u. And so that's 2y equals u. So that means that x equals 4y squared minus a half. And so that is a parabola that's a little thinner, up a half. I'm sorry, this was a fourth here. 1/4. 1/4. So that would be this parabola here. So vertical lines, I mean horizontal lines are, I'll draw them all in blue now. They're all these guys right here. So all the horizontal lines go like that. All the horizontal lines go to those parabolas, and all the vertical lines, I'll draw them in red, all the vertical lines go to these parabolas here. And so it fills in this object. Now, it's much easier to work with a box that's given by u between 0 and 1 and v between 0 and 1 than it is to deal with this transformation here. So the idea is to convert it. All right, now there's going to be a change in area here that's going to be an issue. We'll deal with that in a minute. So let's look at the conversion going the other way. How do you do that? So actually I want to do one that's a little simpler. It's this one, number 9 right here. So what I've drawn is the figure. Let's get this out of the way. Number 9. So here's S, this figure here. It's the filled in triangular region, and we're going to see what is going on over here with this transformation here. T is u squared, y is v. U and v are the coordinates on the left, x and y are the coordinates on the right. So when you look at AC here, I've lettered the points. if you look at AC, that is U equals V. So if I apply that to t here, when u is v, then x is y squared, which is the same thing as square root of x equals y. It's plus or minus, but y can't be negative because then v would be negative, and v is not negative over here. So it's just the top half of it. So that would be this here. So this blue line here, AC, goes to the square root function. There, it stops at 1. Now, when we look at this light blue line here, that is from C to B, V is 1. This is the point 1 there. V is 1, always 1, and then U ranges between 0 and 1. So that means that down here, Y would always be 1, and X ranges between 0 and 1. It doesn't matter that some of those points are different. So when X goes between 0 and 1 and Y is always 1, that would be this line right here. Y is always 1. And now if we look at, let's pick a different color, magenta, this line right there, in that case, U is always 0, and V ranges between 0 and 1. So if we take that down here with the transformation, when U is always 0, X would be 0, and then Y would be between 0 and 1. So that would be this line right there. So I'm going to call this region R. So T takes S and it converts it to R like that. So if you look, S is easier to deal with, like integration and stuff, than R would be. So if I want to find the area of S, it's much easier to find the area of S when at base times height than it is to find R. Here we have to use integration, which isn't a hard integration, but it's certainly harder than just 1/2 base times height that's on the left. So now the question might be, well, how do you take the region on the right over to the left? In other words, the pullback, the inverse transformation, what does that look like, and how do you do that? Well, what you do is you just solve for x and y down here. You solve for u and v in terms of x and y. So if you look, x is always u squared and y is always v. So it's real simple. U is the square root of x. It's the positive, it's not plus or minus, because if you look up top here, u is always positive in this in the triangle. Triangle, u is always positive. And then v is just y. And so the pullback says, okay, for every x value I have in this region here, for every x value, u is going to be the square root of x. And for every y value, v is going to be the exact same y value. So you can work with that as well. All right, so this would be the pullback, the inverse transformation here. So the transformation t will be x and y solve for. The inverse transformation will be u and v solve for.